Greetings and welcome to Distillate. In the previous class, we discussed about crystallization. So in crystallization, we discussed that if we have a crystallizer, suppose this is my crystallizer, then the feed solution is fed to this crystallizer. Let's say it has mole fraction XF. All right. Now, this crystallizer, what it does is it super saturates this feed solution. So it super saturates your feed solution. All right. And from its super saturated state, it comes to its saturated state. All right. It comes to its saturated state. So while it comes from super saturated to saturated state, it releases solids, or basically it releases solute. Okay, the solute, it moves out of the solvent, and this solute, it is separated as crystals. All right, and then after the solute gets separated, whatever is the remaining solution, that is your mother liquor. All right, that is your mother liquor. All right. So most of the times mother liquor is saturated. Okay, most of the time it is saturated, unless we use certain mechanism to remove the solute from the saturated solution as well. If we don't do that, or if suppose we increase the temperature or something, then it would not be saturated anymore. All right, but let's say if we do not do anything else, then we can get mother liquor as saturated. So mother liquor comes out from here with XL as the mole fraction of the mole or mass fraction of the solution in the mother liquor. And here we get crystals with XC as the mole mass fraction or mole fraction of the crystals, solid in the crystal. So now, in order to calculate XC, we have another thing. So in order to calculate XC, what we are going to do, if we have an anhydrous crystal, all right, if we have an anhydrous crystal, for example, yesterday we discussed magnesium sulfate. So in anhydrous crystals, Xc is always going to be equal to 1. All right. If the crystal is hydrated in nature, for example, let's say you're taking MgS of 4.7H2. All right. So if you're taking this, then in that case, your Xc is going to be molecular weight of anhydrous crystal, that is MgSO4, upon the molecular weight of hydrated MgSO4 .7H2, right? Hydrated crystal. All right. So that's going to be Xc. So that's how you calculate Xc. Then you, of course, form the overall material balance equation. That is F is equal to L plus C. Usually it's also accompanied by evaporation. So here Xc is 0, of course. So the overall material balance equation that is formed is F is equal to L plus C plus E. And the component balance equation is going to be Xf into F is equal to Xl into L plus Xc into C. All right. So that's how you form these equations and solve the problems. All right. So this is what was crystallization. Hope you people are clear with crystallization. Please concentrate a bit more on crystallization because it's generally quite asked in the examination. All right, in the GATE exam, it's asked. So please try to concentrate a bit more on crystallization. So if you're not clear with the concepts of crystallization, then please go back and look at the previous video. All right. So in today's lecture, we are going to deal with drying. All right. Drying is another very important unit operation that takes place in the chemical industry. So what happens in drying? We have wet solid that is brought in contact with dry air. All right. So wet solid, it is brought in contact with dry air. What happens is when this wet solid, it comes in contact with dry air. This wet solid, of course, it has dry solid, that is only solid with no moisture, and water. All right. So what happens when it comes in contact with dry air, then this dry air either takes some of this moisture or takes all of this moisture away. All right. And since now dry air has moisture in it, therefore it becomes wet air. So that wet air is nothing but your dry air plus the moisture that it has taken from the wet solid. Okay, that it has taken from wet solid. All right. And whatever we get is our dry solid, which is of course wet solid minus moisture lost to dry air. All right, moisture that has been lost to air. All right. So drying is quite easy. While we come to material balance, it's quite easy to use material balance for drying. I'll give you a way of solving drying problems quite easily. That way you'll not have too much of an issue while you've solved drying related problems. All right. So when we'll be solving problems, I'll get to that. All right. So the wet solid goes out as dry solid. Now this dry solid, as I told you, it still might contain some moisture, but that moisture would definitely be lesser than what it initially contained. So let's say it contained 80% moisture here. So it might contain around 15% or 20% moisture here, something like that. So the moisture content, I'll not use that word, the mole fraction or mass fraction of moisture in the wet solid, it would reduce. All right. So that's how drying operation takes place. By coming drying, in that case, you have wet solid that comes in contact with the dry air. All right. So now you all must have noticed that in drying as well as evaporation, drying as well as another unit operation that you studied, that was evaporation. In these two unit operations, we saw that ultimately water is being lost from the unit. Correct. Even in evaporation, this happened that we had the feed and you had water that left in the form of E, right? And similarly here, this water is being lost, although it's being lost to dry air, but still water is being lost. So what is the difference between evaporation and drying? So the major difference between evaporation and drying is the dominant phase. All right, dominant phase. So when we talk about evaporation, in that you have liquid phase which is dominant. All right, you'll always find evaporation taking place from a feed solution. All right, feed solution is liquid, right? It's liquid. So liquid phase is dominant in case of evaporation, while in case of drying, solid phase is dominant. So in evaporation, whatever water or moisture is lost, that is lost from the liquid phase, while in case of drying, whatever moisture is lost, that is lost from the solid phase. All right. So for example, if you see water being lost from water bodies, swimming pools, etc., that is characterized as evaporation. Why? Because over here you have liquid. Liquid, that is the dominant phase, right? But if let's say you wash your clothes and allow them to lose water in sun, that is characterized as drying. All right, because in drying, that cloth that you have, that cloth is solid. That is your solid phase. All right. So since it's a solid phase, that is why this cloth is going to, when it loses moisture, that comes under the category of drying. All right, that comes as drying. So that is not evaporation. All right, keep this in mind. Okay. So since we have now understood the concepts of drying, so now let's solve this problem. So in a paper manufacturing industry, the pulp has to be dried from 50% to 10% weight by weight. That means weight percent. If in one day 15 tons of paper is fed to this drying unit, how much water would be removed per day? So let's first of all draw our block diagram. So block diagram, we have a dryer. We have our feed. We have, let's say, dried product, let's call it P. All right. And then water lost, for now, I'll just call it as E. All right. Although, again, I'm telling you, this is not same as evaporation. This water is lost with air, but I don't want to unnecessarily add streams to your block diagram. And always remember, whenever you're drawing a block diagram, don't unnecessarily add streams. There has been nothing mentioned about air, nothing. So please don't unnecessarily draw air over here. All right, that I'm drawing air stream or something. Don't. Otherwise, it would only make your block diagram more confusing, and you'll find it difficult to solve these problems. All right, so don't unnecessarily draw block diagrams where you have streams which have no use, right? So here they have told that they are losing water, so I have simply made a stream that shows that water is being lost, nothing else. All right, so in a paper manufacturing industry, the pulp has to be dried from 50%. So my XF is 50%, that is 0.5, and my XP is, I think, 10%, so that is 0.1. All right, so this is the mole fraction of water. Remember, this XF is now the mole fraction of water, or mass fraction of water, whatever. All right, so it's not mass fraction of a solid, it is the mass fraction of liquid. Now, why is it mass fraction of liquid? Why is it not mass fraction of solid? So we always, from the first day itself, when we started material balance, I always told you that we have to see that XF should be the mole fraction or mass fraction of the solute. And in the first class, that is when we discussed about the chemical engineering variables. In that class, when I discussed solution, then I told you that solute is the component that has less dominance, and solvent is the component that is available in abundance, abundant component, right? That is my solvent. So what is my abundant component in case of drying? Is it solid or is it liquid? It's obviously solid. That is why we are going to have solid as our solvent in case of drying, and solute would be water. All right, not exactly, but yeah, if you keep it in that manner, then the more abundant component would be the solute, and the less abundant component is going to be water. So this XFXP, now onwards, keep this in mind that whatever this is going to be, this is going to be the mass or mole fraction of the of water. All right, this is going to be mass or mole fraction of water. So with the same logic, XE over here should be 1, correct? Because this is the mass or mole fraction of water now. All right, whatever X's we are going to take, that is going to be for water, right? So this is going to be 1. Remember, don't get confused between evaporation and drying. Evaporation, your abundant component is liquid. In drying, your abundant component is solid. All right. So once we have this with us, so we can simply form different equations for material balance and solve the problem. But as I told you, I'll tell you a trick how to deal with drying problems easily. So let's just understand. See over here, what happens in drying, whatever solid, dry solid, not wet, only dry solid, whatever dry solid is present here, the same amount of dry solid is present here. All right. There is no way that your dry solid is going to be lost. In any case, it is not going to be lost unless and until it's a chemical reaction. It will not be lost. The solid is going to be there itself. All right. So since solid is always constant, it's going to be constant throughout. Therefore, instead of doing anything else, what we can do in drying, we can form the first equation itself for solid balance. All right, what we can form, the first equation itself can be of solid balance. All right, so when we form the first equation for solid balance, that makes it very easy to solve any other problem. any other part of the problem. Right? It becomes very easy. Okay, so for drying, specifically for the unit operation of drying, we are going to form the first equation for solid balance. All right. So let's do solid balance. So what is solid over here? 1 minus xf, that is 0.5. Input solid is equal to output solid. Correct? There is no solid in the lost water stream. So this is going to be the only equation. So what is xf? Xf is 0.5. So this is going to be 0.5f. And xp is 0.1. So this is going to be 0.9p. Right? So now we already know that 15 tons are fed per day. This is 15 tons. Let's not unnecessarily change the unit. So 15 tons, 15 tons. So this is going to be 0.5 into 15 is equal to 0.9 into P. Correct? 0.5 into 15 is equal to 0.9 into P. So from here, you will get P is equal to 0.5 into 15 upon 0.9. All right. So when we calculate this value, it is going to be 8.33. 8.33 tons. All right. This value is going to be 8.33 tons. Okay. Once we get P as 8.33 tons, we have to calculate how much water is removed per day. So we are going to now make an overall material balance equation. So after solid balance, we are going to make overall material balance. So overall material balance is going to be F is equal to E plus P. Hence water lost E is equal to F minus P, that is equal to 15 minus 8.33. All right. So that is going to be equal to 6.67 tons. All right. This is the amount of moisture that has been lost, or this is the amount of water that has been lost per day. Okay. Per day. Clear? Hope you people could understand this problem. So please remember, while we are doing drying problems, the first equation that needs to be formed is always of solid balance, and then you need to do overall material balance. So since we are done with this, now you can go ahead, pause the video, and try to solve this problem yourself. Hope you could solve this problem yourself. If you couldn't, then let's have a look. A dried fabric contains 5% moisture. The fabric initially contained 48% moisture. The amount of water moved to obtain 1000 kg of dried fabric. Similar to what we did in the previous question. Same way, you have to draw the block diagram. You have to draw the block diagram. This is going to be your dryer. And here we are going to have our F feed. And this is our product. So in the previous question, they had given us the feed, and they had asked us to calculate E. And this time they have given us the product. So that doesn't really change a lot. Product is given to be 1000 kg, and XP is 0.05. So because it contains 5% moisture, and XF is 0.48. All right. So first of all, as I told you, we are going to do solid balance. So for the solid balance equation, so the solid balance equation gives us 1 minus xf into f is equal to 1 minus xp into p. So this is going to be 0.52f is equal to 0.95 into 1000. Right? So from here, we get F is equal to 0.95 into 1000 upon 0.52. So that is going to be equal to approximately 1827 kg. All right, 1827 kg. Hence, when we form the overall material balance equation, then we are going to get F is equal to E plus P. Hence, E is going to be F minus P. That is 1827. 1827 minus 1000. That is 827 kg. All right. This is the amount of moisture removed. All right. Next, we move on to example number 6. Go ahead, pause the video and try to solve this problem yourself. Hope you could solve this problem. If you could not, then let's have a look at this problem. A dryer is fed with wet solid to reduce the moisture content from 80% to 15%. So this is my dryer. This is my dryer. It is fed with wet solid to reduce moisture content from 80% to 15%. 0.8 to, let's say, we call it P. So XP is 0.15. All right. Then they are saying that the product leaving the dryer is admitted to an oven, which further brings down the moisture content to 2%. So this P is further fed to an oven, and this oven, it further brings down the moisture content to 2%, right? So let's call the product leaving the oven be D, and XD is 0.02. 2%. So of course, there would be some moisture that would have left here E1 and some moisture that would have left here E2, right? So let's now see if the dryer can handle 1000 kg of wet solid per day. So this is 1000 kg of wet solid per day. The weight of products leaving the dryer and the weight of products leaving the oven per day. These have to be calculated. And further, you also need to calculate the percentage of the original water that is removed in the dryer and the oven. All right. So percentage of the original water, but okay, we'll come back to that later. First of all, let's see how to solve part number A. So in order to do that, we are going to, this is multiple units. So we are going to draw a control volume or a green box. All right. So we'll draw a green box. And we are going to make a green block diagram for the same. So this is my system. So in this system, I have F equals to 1000 kg. XF is given to be 0.8. Then over here, E1 has been lost. P I'll not mention because it is unit to unit transfer. So it would not be mentioned in the green diagram. Then E2 and then again D with XD equals to 0.0. So now you all know what has to be done. The first thing that you have to do is solid balance. All right. So I'm going to do solid balance now. So the solid balance is 1 minus XF into F, solid input, is equal to 1 minus XD into D. Right? So XF is 0.8. So this is going to be 0.2. F is 1000. So 0.2 into 1000. And XD is 0.02. So this is going to be 0.98. And then of course, this has to be calculated. So we'll get D equals to 0.2 into 1000 upon 0.9. So this D comes out to be 204.1 kg. All right. This is the amount of dried solid that is leaving the oven. All right. Then we need to find P, that is the amount of weight of products that are leaving the dryer. This is the weight of product that is leaving the oven. Then we have to find the weight of products that are leaving the dryer. So for that, we are now going to draw the material balance diagram for dryer, right? So block diagram for dryer. This is my dryer. All right. I'll have F over here again. F is 1000 kg. XF is 0.8 and P is okay, P has to be calculated and XP is 0.15. All right, then this is even. Okay, this is my even. So now when we do solid balance for this diagram, okay, so let me use another color for solid balance for this diagram. So solid balance would give us 1 minus xf into f is equal to 1 minus xp into p, right? So this is going to be 0.2f. 0.2f is equal to 0.85 p. All right. So from here we get p is equal to 0.2 into 1000 upon 0.85. All right. So this is equal to 235.3 kg. All right, 235.3 kg. This is the product, the weight of the products leaving the dryer. All right, weight of the products leaving the dryer. Okay, so this was part A. Okay, you had to find D and you had to find P. All right, so once that is done, then we move on to part B. So part B is about water percentage of original water that is leaving the dryer and percentage of original water that is leaving the oven. So first of all, that means we need to find E1 and E2. So what we are going to do, we are going to conduct overall material balance for dryer. So when we do that, we have F is equal to E1 plus P. All right. So from here, we'll get E1 is equal to F minus P, that is equal to 764.7 kg. All right. P we have already calculated and F was 1000. So this is going to be 764.7 kg. All right. Then next what we are going to do is we are going to draw a block diagram for, or let's take the green diagram itself. So when we do a green block overall material balance about the green diagram, so that is going to be F is equal to output E1 plus E1 plus E2 plus D. All right. So when we do that, we get E2 is equal to F minus E1 minus D. So F also we know, E1 also we know, and D also we know. So from this we get 31.2 kg. E2 we get as 31.2 kg. So now once we have calculated the amount of water that has left the dryer as well as the oven, so now we are going to calculate percentage of original water. So for that, let's find out the original water, right? So original water is basically xf into f. xf is the fraction of mass fraction of water that is there in the solid, right? That is there in the feed, basically, right? And the feed is 1000 kg, so it is going to be 0.8 into 1000. That is 800 kg. All right. Original water is 800 kg. Now, percentage of water lost in the dryer is equal to water lost in the dryer, that is 764.7 kg upon 800, that is original water, into 100. That is equal to 95.875%. All right. Then percentage of original water lost in the oven is equal to water lost in the oven, that is 31.2 upon 800 into 100. That is 3.9%. All right. So that's your result. All right. Hope you people have understood this problem. So once we are done with this, go ahead, pause the video and try to solve example number 7 yourself. Hope you could solve this problem, but if not, then please have a look. So it is given, this is a very important problem. So just look at it. The cotton fabric is dried by passing dry air through it. Now here in this block diagram, we'll definitely put dry air because this has information about dry air, right? So here we'll need dry air into the picture, all right? So cotton fabric is dried by passing dry air through it. Dry air is sent into the dryer and wet air is drawn out at the rate of 3600 meter cube per hour. The wet air is maintained at a pressure of 1 atm and 185 degrees Celsius, 185 degree Fahrenheit. Now, if you remember, we discussed about Fahrenheit to Celsius conversion. So just keep this in your mind always, that if you have anything to be converted from Fahrenheit to Celsius, you use this formula. Degree Fahrenheit minus 32 upon 180 is equal to degrees Celsius upon 100. All right, this is the formula that you have to use. So we had 185 degree Fahrenheit. So 185 minus 32 upon 180 is equal to degrees Celsius upon 100. So from here, we'll get degrees Celsius as 85 degrees Celsius. All right. So 85 degrees Celsius, that is nothing but 358 Kelvin, right? That is 358 Kelvin. So this temperature is actually 358 Kelvin. Okay. All right. We'll just mention it there. Now, the wet air contains 10 mole% of water and cotton fabric to be dried contains 85 weight% water. All right. And it leaves the dryer with 15 weight% water. Calculate the mass flow rate of air fed to the dryer and the mass flow rate of cotton fabric leaving the dryer. Remember, this is quite conceptual in nature. This question is quite conceptual in nature. There are a lot of concepts involved. All right. So they have given information about mole fraction, weight fraction. So that's all to confuse you. All right. So let's have a look at this question. So we'll start solving this question using step-by-step approach. So first step is always to draw block diagram. So let's draw block diagram. So we have our dryer. Into this dryer goes feed which has initial weight%, that is 85 weight%. So XF, now here since they are using XF and XF dash both, mole fraction and weight fraction both, so I'm going to use XF dash for weight% and XF for mole%. So XF dash they have given to be 0.85. All right, then P and XP dash they have given, I think 115, yeah, so 0.15. All right, now let's go ahead. The wet air contains 10 mole%. So from here we get dry air from the bottom. I'll represent it with a different color. So from here we get dry air. All right, D, and from here we get wet air, W. Okay, and the mole percent is 0.1. All right, and obviously this is dry air, so this will have no water at all. So we'll get XD as 0. This is mole percent, that is why no dash. All right, remember. So now, as we all know, first equation we are going to form for solid balance. All right. Any information has not been, yeah. So solid balance, the first equation that we are going to form is for solid balance. So that would be 1 minus xf dash into f is equal to 1 minus xp dash into p. So we'll get 0.15 f is equal to 0.85 into p. All right, keep this as equation number 1 because we don't have f and p, so we'll just keep this, or let's not keep this equation, keep the next one, 0.15 f minus 0.85 p is equal to 0. This is my equation number 1. All right, so this was the equation that has been obtained by solid balance. All right, now they have given information about air, right? So dry air, it contains no moisture, and wet air, it contains moisture, right? So let's not go to dry moisture balance because moisture is contained in all the 4 streams, so it could be a little complicated. Let's go for dry air balance. So when we go for dry air balance, so dry air balance. So to perform dry air balance, we are going to see dry air over here in the entry point. So that is going to be D. All of the air is dry. And in the exit point, it is 1 minus xw into w, right? 1 minus xw into w. So you get D as 0.9 times w. This is your equation number 2. All right, keep this again in your mind. Now, about air, they have given us information that air is moving out at a flow rate of 3600 meter cube per hour. So this is my volumetric flow rate of air, 3600 meter cube per hour. Pressure they have given as 1 atm. Temperature we just saw, it would be 358 Kelvin. So we have pressure, volume, temperature. Hence we get moles using the ideal gas equation. All right. So molar flow rate of wet air, that we have taken it as W. So W is equal to PV by RT. So that is 1 atm, that is 101.325 kilopascal into 3600 meter cube per hour, right? 3600 meter cube per hour into 1 hour upon 3600 seconds. So this would become meter cube per second. All right, upon R, that we are going to take 8.314 kilojoule per kilomole, that is kilopascal meter cube per kilomole Kelvin, and temperature they have given as 358 Kelvin. So Kelvin, kilopascal, meter cube. Hence, whatever we'll get, that would be in kilomole per second, right? So this is equal to 0.034 kilomole per second. This is W. All right. So if this is W, then of course D is going to be 0.9 into whatever the dry air is going to be, that is going to be 0.9 into 0.034 kilomole per second. All right. So that is going to be equal to 0.0306 kilomole per second. That is what we have got for dry air. All right. Next, now since we have done dry air balance, we have done solid balance, we know D, we know W. So now we finally come to a very complicated equation. All right, before that, let's now we are not going to balance water directly. All right, we are not going to balance water directly because remember this is in mole flow rates. D and W are your molar flow rates, and uh, F and P are mass flow rates. All right, they are mass flow rates. So therefore, we'll have to use the fact that whatever mass of water has been lost by F, that has been gained by W, right? So that has been basically gained by D. All right. So water gained by dry air is equal to 0.1 into W because it did not initially contain anything, right? So now it contains 10% moisture. So that is why this is my water gain, right? So that is 0.0034 kilomole per second. All right. So this 0.1 into W is basically water in wet air minus water in dry air. That is the water that has been gained by dry air. So water in wet air is 0.1 into W and water in dry air is 0 into W. Sorry, 0 into D. So that is 0.1 into W. All right. So that is 0.0034 kilomole per second. This is the water that has been gained by dry air. So if we convert this into mass flow rate, so this is going to be 0.613 kg per second. Now this mass flow rate can be easily used in this equation, FP, right? Because F and P are also my mass flow rates, all right? So now we can simplify this problem as a simple drying problem. This is the mass of water that has been lost, all right? This is my F, this is my mass of water that has been lost, that is E, and this is my P. So over here, now if I use the overall material balance, then that would be F is equal to E plus P, where E is equal to 0.613. Hence, we will get F minus P is equal to 0.613. This is your equation number 3. So you already have equation number 1 in F and P. You already have equation number 3 in F and P. Therefore, we finally get F as, from by solving 1 and 3, we simply get F is equal to 0.744 kg per second, and P, we get it as 0.131 kg per second. All right, 0.131 kg per second. All right. So they had asked you calculate the mass flow rate of air fed to the dryer and the mass flow rate of cotton fabric leaving the dryer. So mass flow rate of cotton fabric leaving the dryer is 0.131 kg per second. That is fine. Now mass flow rate of air fed to the dryer, that is D. So D is nothing but 0.0306. So 0.0306 kilomole per second, right? So what we can do is we can multiply it by the average molecular weight of air, that is 29 kg per kilomole. So that is equal to 0.887 kg per second. All right. So that is my mass flow rate of air that has left the dryer. Most of you must have done this problem wrong because you wouldn't have considered this mole percent and weight percent. You would have taken it the same way, right? But that's not how it has to be done. And again, even when we formed the two equations, one by dry air balance, the other by solid balance, we could not exactly use these two equations together because here dry air and W were in mass in molar flow rates, while over here F and P were in mass flow rates. So first we had to calculate what is the water gained by dryer. Once we get the water that has been gained by dryer, so this water that has been gained by dryer is equal to the water that has been lost by the feed, right? So this water gained is equal to water lost. So this water lost we depict as E in our normal block diagram. So this E we calculated in kg per second, and based on that we did our overall material balance. So we get two equations, equation number 1 and equation number 3. Equation number 1 by solid balance, equation number 3 by overall material balance. So by solving these two equations, we finally get F and P. And to calculate the mass flow rate of dryer, we simply multiply the molar flow rate by the mass or average molecular weight of dryer. Hope you people have understood the unit operation of drying.